I want to show you Descartes' rule of signs today. It's a clever way for a person to determine the possible numbers of positive and negative real zeros for a polynomial, okay? So if you write the polynomial in standard form, it has to be in standard form. So, descending order of powers like we normally would. Then what Descartes' rule of signs does is it uses the number of sign changes of the terms. And by sign changes, I mean a positive term to a negative term would constitute a sign change. So in this example right here, we're looking at the coefficients, right? The coefficients of the terms. So here we have +1, +1, +1, +1. So those are all positive coefficients. Now look, we get a negative coefficient here for our constant, our coefficient of x to the 0. So there's one sign change. Okay, what that tells us is that this function definitely has one positive real zero, guaranteed. It's got one positive real zero. That's going to be helpful to us. You might be thinking, okay, why is that such a big deal? Well, it's going to be a big deal on Wednesday, because Wednesday what I'm going to show you is the rational root theorem. And the rational root theorem tells you, it gives you a method for finding all of the possible rational zeros of a polynomial. It's really cool that we can do this, but the disadvantage is, in certain cases, as you'll see on Wednesday, sometimes there's a pretty long list of possible rational zeros that you're going to have to check. And you can check them synthetically by running them through synthetic division to see if you get zero remainder. And we'll talk about all that stuff on Wednesday. But if you can possibly narrow that list down, that's really a good thing to be able to do, okay? Because sometimes the list can get pretty long. So this tells us that it's got exactly one positive real zero. And I'll tell you, we'll go into how many possible zeros you get based on the number of sign changes in a little more detail in a moment. Okay, the other part of this is we want to know the number of possible negative real zeros. And what you do there is we're going to calculate f of negative x, right? So we had our original function. Now we're going to calculate f of negative x by evaluating f of x at negative x. Well, think what that does. If I'm going to evaluate a function at negative x, what's going to happen for every even power in our polynomial when I evaluate the polynomial at negative x? They stay positive, don't they? Right? You can kind of think of it this way. It's like I'm just switching the x's for negative x's, right? And so we know that the even powers are going to stay positive, but the odd powers are going to flip sign, right? The powers of x become negative. And so we end up with, that's positive, that changes to negative, that's positive, that changes to negative, that stays what it was before, right? Stays negative. So we could have predicted that. Let's see, where's our original example? I'm going the wrong direction, aren't I? So there was our original function. You guys now should be able to say, okay, well, what's f of negative x going to be? Even powers are going to keep the same sign they had in f of x. Odd powers are always going to flip. So this one's going to stay positive. This one's going to flip to a negative x cubed. That's going to keep its previous sign, which is positive. This one's going to flip. This one, really, there's an x to the 0 there, isn't there? So you see that's an even power of x, right? And of course, it's just a constant. So when you switch the x's, it's not going to have any impact on it, is it? Right? That one stays a -1. So when we do that, now what do we find? Well, now we find that there are 3 sign changes for f of negative x. So that's telling us if there are 3 sign changes, that tells us that f of x could have 3 or 1 negative real zeros. How did we get 3 or 1? How come we couldn't get 3 or 2 or 1? Because of the complex conjugate theorem, right? The complex zeros have to come in pairs. And so we know that when we apply Descartes' rule of signs, we always know that it's going to, the number of sign changes gives us the maximum number of positive or real zeros, depending which part we're doing. But then we could also have even increments less than that also, right? So we could say if it's 3, then we can always move down and by 2s, right? That makes sense? Okay. So let's try this then. Well, first of all, here is Descartes' rule of signs in all its glory. And I'll put this right up to the notes. Okay, this isn't in your packet. That doesn't cover Descartes' rule of signs. But I'll put this up in my PDF notes for, that are in your Google Classroom. So if you write the polynomial in standard form, really what we just said, the number of positive real zeros is either equal to the number of sign changes of f of x, or it's less than that number of sign changes by an even integer. Okay, could be 2 less, 4 less, 6 less, etc. Number of negative real zeros is either equal to the number of sign changes of f of negative x, or it's less than that by some even integer amount. Okay, so let's try this. How about this guy? Think about this for a second. We want to determine the possible numbers of positive and negative real zeros. So what do you think? What's the possible number of positive real zeros? Could be 2 or 0, right? Everybody see that? Because I've got 2 sign changes. There's a sign change, and there's a sign change. So the answer is 2 or 0 positive real. Oops, can't spell. Jeez. Okay, makes sense. Okay, so now how about negative? If you need scratch paper, I've got some up here, but maybe you want to just kind of scratch this out in your notebooks. Calculate for me the possible numbers of negative real zeros. So first you'd probably have to write out f of negative x, wouldn't you? So Rebecca, what'd you get for f of negative x? It stays the same, right? You get that? Now, maybe I was a little unclear about that. So the x to the 4th part, that's going to stay the same sign. When I plug a negative x in, the negative x to the 4th is just equal to x to the 4th, isn't it? So the first one is not going to switch signs. That one does switch, so we're going to get positive 3x cubed. Stays the same, so plus 6x squared plus 4x. There you go. So it looks like we got how many sign changes then, everybody? 2. We get a sign change there, and we get a sign change there. So what's our answer? 2 or 0. Okay. And, you know, we can't do much with that now, but starting on Wednesday, we'll be able to go a little further with that. That's going to be, so the first few problems I'll put the assignment up, the 5.8 practice 2 assignment. And I think it's like the first 3 or 4 are just practicing that. And then you're going to get into some stuff that you don't know how to do yet till Wednesday. But you could do those if you wanted to. So I'll put this stuff, here's just a explanation of what we just did. And then there's graphic confirmation, right? If you actually graph this thing, you can see that it does have 2 negative real zeros and 0 positive real zeros. Okay. All right. That's good for today.